So continuing on, okay, suppose I want to measure the height of a mountain. So what I do is I know I'm 2 meters tall, so whatever the height I measure is, I'm going to have to account for that. If I stand at one place, I measure an angle to the top of 35 degrees. Then I move 900 meters closer, and now I measure 47 degrees. So how tall is the mountain? Incidentally, this is how surveying works. So if you learn your trigonometry pretty well and you learn how to use surveying instruments, you can work for the city or a private engineering company as a surveyor, measuring heights, distances, which you then use to compute areas and lengths, and you place boundaries for like property tax assessments, and it's considered a fairly skilled profession. Okay. But anyway, we have two different angular measurements separated by 900 meters, so can you find the height? So here's basically what we got. Our height is going to be determined by the height of this triangle plus an extra 2 meters. So don't forget that you have height, and when you're actually a surveyor, the height of your surveying instrument is quite important. And what we know is I can measure 35 degrees here, but if I move 900 meters closer, I can measure 47 degrees there. And now we've labeled a bunch of stuff. They've put capital A and C in the skinny triangle off to the left. Okay, but observe that if this angle is now capital B, in one triangle, the side length B across from it would be this. In the other triangle, it'll be this. And we measure heights of objects perpendicular to the ground. Okay, so I assume I'm measuring the height of the mountain relative to a straight line going down. Okay, so the first thing to do is start filling in angles. That's what we have more information about, right? I have two angles, so let's use that information. So since across from C is 47 degrees, C itself must be 133. Good. Also, in that skinny triangle, now that I have C is 133 degrees and I have another angle of 35, I can find the missing angle. Notice in the skinny triangle, by the way, we now have this. I know this angle, I know this angle, and I know this side. So we have angle, side, angle. So using the law of sines, I can complete this triangle. And that's basically what we're going to do. Now that we have two angles, we're going to find this skinny little angle C. It's just 12 degrees. Now we're going to start completing that triangle, the skinny one off to the left. So use the law of sines to find the missing length. And it's about 3,165. Great. Now we can skip right to the larger right triangle. So ignore the skinny triangle, we're done with it. Okay. So we had an angle of 35 degrees here. We had 900 meters here, but that information is now kind of useless to us. We're trying to find the unknown height, but we just determined that this length was, I think, 3,165 point something. But now we have a right triangle. Okay. So the sine of 35 degrees will be opposite over hypotenuse, 3,165.86. So solving for the missing height, which, yeah, on the other slide, this was labeled as C rather than H for height, we get about 1,816 meters. So don't forget that you're 2 meters tall, so it's about 818 meters tall. So notice we used the law of sines just to get one piece, the hypotenuse of the big triangle, and then we used simpler work, just right angle trigonometry, in order to complete for the height of the mountain. As I've mentioned, once you learn one skill, you can then use it as a single step in other problems. So this problem put together stuff from section 8.1, but also here from section 8.2. And that's totally reasonable, okay? A problem on an exam might combine techniques from different sections. So how about another example? Okay, we've got a picture with lots of extra coloring on it. That's going to make things tough to read. So we have a Coast Guard station, Zulu. There it is. It is 100 miles due west of this station, X-ray. Awesome. So a ship sends out an SOS call. Okay. So it's just like a radio beacon going off. So what each station can do is measure what's the angle to that signal. So Zulu says, I have an angle of 50 degrees east of north. So there it is in this diagram, whereas X-ray says I have 60 degrees west of north. where is the ship, basically? So what we're going to do now is what's called triangulate a signal. If the same radio signal is picked up by two different places, if they can determine a direction to the signal, and they know the distance between them. So what was important is that we already know the distance between these two objects. So using two directions and one distance, we can triangulate the position of the object. So, the next time you're watching CSI or whatever, and someone rushes to the computer to go like, we need to triangulate their position, this is what they're doing. Okay? They're using two directions and one fixed distance in between the observation posts to determine where something is. And then we have this little word problem at the end. If a helicopter can fly 200 miles per hour, how long will it take to get there? Well, we just need to know how far away it is. All right. So here's the figure with all the same stuff marked. So we complete a triangle out to the ship. Now, the first thing we had to do was, this angle was given to be 50 degrees west of north, which means this angle here is 40 degrees. And since this was given to be 60, this is 30. So we have complementary angles inside the triangle, which we use to find angle C. It's 110 degrees. And now notice we have all of the angles and one of the sides. So I can use the law of sines to find the missing sides. That'll tell us which station it's closer to, by the way. So you use the law of sines and get that it's about 68.4 miles from the angle A station. I forget which one that was. And it's 53.2 miles from the other one. So station B, which I guess was Zulu, is 53 miles away, whereas station X-ray, which I guess was A, is about 68 miles away. And then to find the time it takes a helicopter to get there, that's pretty straightforward. We're going to use, of course, the shorter distance. We want our rescue helicopter to get there soon. And time is just distance over speed. The distance was 53.21 miles. The speed was 200 miles per hour, so that's about a quarter of an hour or a little over 15 minutes, 16 minutes. So the helicopter can arrive in 16 minutes if it leaves right now. And the ship doesn't move. Okay, so the main thing of this section was the law of sines. If you know two angles and one side, then you know all three angles and one side, and then the law of sines can be used to complete a triangle. And then we used some applications of that. We combined it with some traditional right angle trigonometry for the mountain word problem, and we combined it with simple time is equal to distance over speed computations in the second example. In the next section, we're going to come in and learn the law of cosines, which is how you solve triangles where instead of being given two angles and one side, you're given two sides and one angle. With the exception of side-side angle, that is the ambiguous case, and that's where you use the law of sines, and you might have no solutions, one solutions, or two solutions. But if you have two sides and one angle, where the angle is in between, side angle, side congruence, or you have all three sides, that's the law of cosines, and that's the next section.